Light is arriving from places it should never have come from. The universe follows rules about how things move through space. One of the most fundamental is that light, despite traveling faster than anything else in existence, still obeys the geometry of the space it crosses. It follows the shortest available path. It bends when mass curves space-time around it. Astronomers have known this for over a century, and the mathematics behind it holds up across every environment where it has been tested. When light passes near a massive object, the trajectory shifts by a calculable amount. The shift is predictable. The geometry is exact. Gravitational lensing, the process by which mass bends the path of light, is one of the most verified predictions in modern physics. When a galaxy cluster sits between a distant light source and an observer on Earth, the cluster's mass acts as a lens. The light curves around it. The source appears displaced, stretched, or multiplied. Astronomers can model the mass distribution of the lensing object, trace the expected deflection angles, and reconstruct where the original source should appear. For most systems, this process works cleanly. The math matches the observation. The model holds. Then there are the cases where it does not. Across several galactic-scale lensing systems, the images that appear in our instruments do not match the images that should appear given the known mass distributions. Light arrives at angles that cannot be accounted for by the visible matter in the lens. Arcs form in locations that the gravitational geometry does not predict. Multiply image sources appear offset from their expected positions by margins that, in some cases, exceed what any reasonable mass model can accommodate. The warped image signatures themselves, the stretched arcs, the Einstein rings, the split quasar images, carry distortions that suggest the light has passed through a curved trajectory field with a geometry that does not correspond to any mass the instruments can detect. Light is traveling along paths that look impossible. Two competing frameworks have emerged to account for this. They do not agree with each other, and neither one closes the problem completely. The first framework attributes the anomalous deflection to dark matter, mass that interacts gravitationally but emits no light and remains undetectable through any electromagnetic observation. Under this framework, the visible mass in a galaxy cluster is only a fraction of the total gravitational influence. Invisible halos of dark matter extend far beyond the luminous regions, and their geometry determines the actual shape of the lens. The observed deflection angles that exceed what visible matter predicts are not anomalous at all. They are simply evidence that most of the lensing mass is hidden. This framework has substantial supporting evidence. Galaxy rotation curves, the speeds at which stars orbit the centers of their galaxies, have long indicated the presence of mass beyond what can be seen. Simulations of large-scale structure formation, which trace how the universe evolved from its early smooth state into the current web of filaments and voids, require dark matter to produce distributions that match what astronomers observe. The Bullet Cluster, a system of two galaxy clusters that collided and passed through each other, shows a spatial separation between the visible gas, slowed by the collision, and the gravitational center of mass, which continued forward as if unimpeded. Something was there that the gas was not. The dark matter explanation for anomalous lensing is not peripheral. It sits at the core of the standard cosmological model, but the explanation has a problem that does not resolve cleanly. The specific predictions of dark matter lensing depend on the assumed distribution of that dark matter, its density profile, its radial extent, its concentration. These parameters are not directly observable. They are inferred from the lensing itself, which means the model risks becoming circular. The anomalous deflection is explained by dark matter whose properties are defined by the anomalous deflection. Independent constraints exist, drawn from rotation curves and simulations. But when these constraints are applied to specific lensing systems, the predicted image positions still disagree with the observed ones by amounts that are difficult to dismiss as measurement error. In some systems, the offsets are too large and too systematic to attribute to uncertainty in the dark matter distribution. The model accommodates the general pattern. It does not always reproduce the details. No direct detection of dark matter has been confirmed in any laboratory. The second framework approaches the problem differently. Rather than attributing the anomalous deflection to undetected mass, it proposes that the gravitational law itself behaves differently at low accelerations, the regime that characterizes galactic and intergalactic scales. Modified Newtonian dynamics and its relativistic extensions posit that the effective gravitational force experienced by an object does not follow the standard inverse square relationship below a certain threshold acceleration. At the scales where galactic rotation curves diverge from Newtonian predictions, the modification kicks in and produces the observed behavior without requiring any additional mass. This framework reproduces certain observational patterns with notable precision. The Tully-Fisher relation, an empirical correlation between the luminosity of a spiral galaxy and the speed of its outermost stars, follows directly from the modified dynamics, with a predictive accuracy that the dark matter framework struggles to match from first principles. For isolated galaxies where the dark matter distribution can be constrained independently, the modified dynamics sometimes produces better image position predictions than dark matter models calibrated to the same systems. The framework does not require postulating invisible mass whose properties can be adjusted to fit the data. The lensing geometry under modified dynamics is not identical to the lensing geometry under general relativity with additional mass. The deflection of light in the modified framework depends on the relativistic extension chosen, and several such extensions exist with different mathematical structures. Some reproduce the anomalous arcs more accurately in specific systems. Others fail where the dark matter explanation succeeds. No single relativistic modification of gravity has been demonstrated to work across all observed lensing configurations simultaneously. The two frameworks converge on different predictions in exactly the systems where the data is most ambiguous. Where the bullet cluster appears to support dark matter, the spatial separation of the gravitational center from the visible gas, the modified dynamics framework faces genuine difficulty. The offset is large. Reproducing it without additional mass requires either a particular choice of relativistic extension or additional assumptions about the intergalactic medium that are themselves difficult to verify. Modified dynamics proponents have proposed mechanisms, but none has achieved broad acceptance, and the bullet cluster remains a contested data point rather than a resolved one. Where isolated lensing systems support modified dynamics, the precise arc positions that dark matter models miss. Dark matter proponents respond that the discrepancy reflects inadequate modeling of the dark matter distribution rather than a failure of the underlying framework. The halo parameters are uncertain. More detailed simulations, incorporating baryonic feedback and the interaction between dark matter and visible matter, may close the gap. Whether this is a genuine path to resolution or a post hoc adjustment is not yet determinable. Neither framework is falsified. Neither framework is confirmed at the level required to retire the other. The specific problem the lensing observations pose is not simply that two theories disagree. The problem is that the observable, the image signature, the arc position, the deflection angle, is produced by the geometry of space-time, and the geometry of space-time cannot be directly measured. It can only be inferred from the behavior of light. When that behavior deviates from expectation, the deviation could indicate undetected mass shaping the geometry, or a modification to the law governing how geometry responds to mass, or an as-yet uncharacterized combination of both. The observation itself does not specify which interpretation is correct. The light carries the imprint of the geometry it traversed, but the geometry is not directly accessible. What cannot currently be done is to construct a mass model for a lensing system from independent observations with sufficient precision to rule out either framework at the required level of certainty. The dark matter distribution is inferred, not measured. The modification parameters in alternative frameworks depend on choices about which relativistic extension to apply. Both interpretations involve assumptions that are physically motivated, but not independently verified for each specific system where the anomaly appears. The deflection angles that produce the impossible-looking trajectories exist within a band of uncertainty wide enough for both frameworks to fit plausibly, narrow enough that neither fits comfortably. There is a boundary in this problem that current instrumentation does not cross. On one side of it, the behavior of light is recorded with precision. On the other side, the side that would explain what is shaping the trajectory field, the instruments go silent. The mass distribution that determines the geometry is not directly observable. The modification to gravity that might replace it cannot be tested in a regime where the two frameworks predict the same outcome. The warped image signatures are real. The conflict between what is observed and what either explanation fully predicts is real. The underlying cause remains on the other side of what can currently be reached.